In this vast universe, there is something both weird and interesting. Welcome to the enigmatic world of black holes. These cosmic behemoths are born from the depths of massive stars. As these stars approach the end of their life cycle, they undergo a spectacular explosion and transform into a profound darkness, a place that consumes everything in their path, regardless of size. It's an insatiable force that never stops. In this journey, we will explore this phenomena and satisfy our curiosity along the way. We will start from the stellar mass black holes lurking in space to the monstrous supermassive ones that hold entire galaxies in their grip. Prepare yourself for an exploration of one of the most mysterious phenomena the universe has to offer. We'll delve into their formation, unimaginable properties, and the profound impact they have on the universe. A black hole is essentially a hole in space that devours everything. It possesses a gravitational force so formidable that even light, the fastest traveler in the universe at 300 kilometers per second, struggles to find a way out. This gravitational grip stretches its invisible arms over a defined expanse, rendering the black hole unseen and shrouded in darkness for distant observers. The black hole acts as an insatiable trap, trapping everything within a certain distance, making it invisible and dark. It encounters no difficulty in consuming a variety of objects, ranging from small particles like gas and dust to even large entities such as planets, stars, and even fellow black holes. So the question is, how does such a monstrous entity come into existence? When a star is born, it experiences a force known as gravity, which tries to pull everything toward the center of the star. This is a natural law for objects with mass. Simultaneously, the star undergoes another force known as nuclear fusion, which continually converts hydrogen into helium in its core, releasing a huge amount of energy. This radiant energy serves as the luminous source of light and heat essential for our everyday existence. Throughout the star's life, a delicate balance is maintained between these two opposing forces. Gravity acts like an insistent hand, drawing matter inward, while nuclear fusion functions as a formidable energy source, pushing things outward against the force of gravity. It's a constant cosmic struggle. However, when the hydrogen fuel in the star's core runs out, this delicate balance is disrupted, and the nuclear fusion loses its pushing effect. Then, gravity begins to assert its dominance. For smaller stars, this transition manifests as an expansion of outer layers, transforming the star into a red giant before shedding its outer layers to become a compact white star, known as white dwarf. In more massive stars, a spectacular process called supernova occurs. Gravity starts to pull the material inside the star massively, leading to a huge collapse. If the remaining core mass is medium, protons and electrons may fuse together to create a dense neutron star. But for stars around 20 times the mass of our Sun, an extraordinary fate awaits. A gravitational collapse happens, and matter starts to inexorably move toward a singular point, giving rise to the creation of an entity of unparalleled density and an infinite abyss known as the black hole. Black holes have various features that collectively contribute to their behavior and characteristics, making them powerful cosmic entities in the universe. The fundamental components defining a black hole include the accretion disk, photon sphere, event horizon, singularity, and the relativistic jet. To understand these components, let's delve into an example. Imagine you have a super duper powerful telescope to observe a black hole. But guess what? There's no big black hole staring back at you. Instead, there's this glowing stuff circling around an invisible center. The invisible region is the black hole, while the radiant circle is known as the accretion disk, formed from a nearby star or gas cloud that spirals towards the black hole due to its gravitational pull. The elements within the accretion disk move at incredible speeds, gaining high energy. Subsequently, due to rotational forces, magnetic fields, X-rays, and other factors, certain particles adopt a specific direction, forming a jet known as the relativistic jet. By carrying the high energy amassed in the accretion disk, the jet shoots out into space, appearing as a massive beam, resulting from the conversion of the high energy gained by the particles in the accretion disk into a straight outward motion. Additionally, you're going to notice a distinctive circular ring of light surrounds the black hole near the accretion disk. This is the photon sphere. It is basically a group of photons orbiting the black hole in a continuous loop. Their rotation occurs due to the profound distortion of space-time caused by the immense gravitational pull. You can imagine these photons as cars moving forward, but suddenly they start turning left continuously, as if some mysterious force compelling them into a circular motion. This force is the ergosphere, a region outside the event horizon where the black hole's rotation bends and twists space-time, causing photons within this zone to rotate within the black hole. Under certain conditions, the photon may gradually move towards the black hole and eventually leading it to enter and join the darkness. But in different scenarios, photons may break free from the photon sphere and move away from the black hole. This can happen if photons receive additional energy from external sources, such as interactions with a gas cloud or absorption of radiation from a nearby star, allowing them to escape the gravitational influence of the black hole and move far into space. Now, let's redirect our attention to an even more mysterious boundary, the black hole's door, known as the event horizon. Picture the event horizon as a boundary encircling the black hole. What sets it apart is its uniqueness. Once anything crosses this threshold and approaches the black hole too closely, it disappears forever. It's more like a cosmic boundary that marks the limit where our understanding of physics begins to break down. Imagine you're watching a friend wearing a big clock in his back getting closer to the black hole. As they approach, something strange happens. It's like watching a slow-motion movie, but weirder. You notice your friend's watch, ticking away happily, but as they edge closer to the black hole, time starts to slow. It's as if the black hole is playing with time itself. The closer your friend gets, the more time seems to slow down for them. You see them reaching the edge of the black hole, and suddenly, it's as if they've hit pause. They are frozen in time, right at the edge. From your perspective, it looks like your friend has stopped moving entirely. It's not that they decided to take a break or got stuck. It's the black hole's gravitational magic at work. The immense gravity near the black hole is bending time itself. However, from your friend's perspective, the black hole's gravity is insanely strong. It starts pulling them in a crazy gravitational force like nothing else. It becomes so intense that your friend gets stretched and squished. And because of the gravitational gradient, different parts of your friend's body experience different amounts of gravity. The side of them facing the black hole feels a stronger pull than the side facing away. This causes what scientists call tidal forces. These tidal forces stretch and distort his body. The side closer to the black hole gets pulled more strongly than the other side. This is what we refer to as spaghettification. It's like pulling on both ends, making them longer and thinner. As your friend goes further toward the black hole, the gravitational pull becomes incredibly intense. The difference in gravity between their head and feet becomes so extreme that it leads to severe stretching and compression along their length. Eventually, the forces become so extreme that your friend gets stretched into a long, thin shape resembling spaghetti. This process is both fascinating and quite violent, as the gravitational forces are powerful enough to overcome the structural integrity of your friend's body. Then your friend vanishes into the black hole's heart, known as the Singularity. It's a hidden, dark grasp and a point of a very high density and unimaginable gravitational pull. To simplify it, imagine you have something really heavy, like a bunch of food, and you press on it really hard. You can feel the force when you press on it, right? Now, if that thing is big and heavy enough, like a star, something weird can happen. Its center, or the inside part, gets squeezed a lot, so much that it becomes a very, very tiny point. The singularity in the black hole is that incredibly tiny point. It's where all the stuff in the black hole is squished massively, where the laws of physics as we understand them break down. The journey your friend takes toward this world is like a one-way ticket into the unknown. His body now is being compressed and squeezed into an incredibly small and dense space, where the ordinary rules of space-time and even the human body cease to apply. But this is just the beginning of the black hole story. Black holes grow over time by consuming matter. It's like an expanding snowball, gathering more snow as it rolls. As a black hole consumes more, it becomes heavier, and its gravitational pull strengthens. As we venture deeper into the cosmos, we encounter a diverse family of black holes, each with its unique size and age. The smaller ones, known as stellar mass black holes, are only a few times heavier than our Sun. They are relatively small, with masses ranging from about 3 to 10 times that of the Sun, and are considered to be nearly spherical in shape. Moving up in size, we come across a category of black holes with masses ranging from 100 to 1,000 times that of the Sun, referred to as intermediate black holes. These are expected to have roughly spherical shapes similar to stellar mass black holes. The massive ones are called supermassive black holes. These giants can have masses ranging from hundreds of thousands to billions of times that of the Sun. Unlike their smaller counterparts, supermassive black holes are generally oblate spheroids, meaning they are flattened at the poles and bulging at the equator due to their rotation. Just as your friend's journey transformed into a singular point of high density, black holes also have a life cycle. But, unlike us, they take a really, really long time to die. Their death begins when they start losing some of their mass, a phenomenon known as Hawking radiation. Picture this as tiny particle pairs that spontaneously appear near the event horizon. One particle boasts positive energy, while its partner carries negative energy. They dance together briefly, then vanish. However, on occasion, one of them becomes absorbed by the black hole, while the other escapes, evolving into a real particle in the universe. These particles derive their life force from the energy of the black hole, as that's where they were born. Consequently, they take some of the black hole's energy, and since energy equals mass, the black hole loses a fraction of its mass. This process unfolds gradually over a long time, but it makes black holes, bit by bit, losing their mass until they fade away into the cosmic abyss. We've delved into the crazy world of black holes, uncovering a wealth of knowledge, yet the cosmic mysteries continue to unfold. Our exploration has been a captivating journey through these celestial behemoths, and we sincerely thank you for joining us. Stay tuned for more exciting science adventures, and we look forward to having you with us in the upcoming videos. Until then, see you in the next cosmic exploration.